Okay, hello everyone.
Hi, sir. I have a question.
Yes.
When's the next test?
Let's see. Good question. It's set for the 29th, which is next Thursday. However, we're really just going to have to see where we get on this. Yeah, I mean, I'd like to keep it there, but we just obviously will not cover all of this material on that test. So
Okay.
let's see how this week goes, and then but let's plan on it being on the 29th.
Okay. And so I'm guessing exam 4 on the grade book is going to be the final.
Yes, that's the final.
Okay.
Mhm.
Thank you.
Okay, no problem.
So just a quick question. You're not allowed to like cut out any topics to save us time, right? Like you have to do them all.
Well, I mean, I'm not supposed to, but you know, we lost a week because of the weather, and so you know, there's not a whole lot that I can do without going at such an accelerated speed that you're not learning. You know what I'm saying?
Right.
So I'll do my best, and then you know, whatever I don't cover, I'll probably just give you a link to some videos in case you, well, if you want to watch those before you go into Cal 2, you know, for things we don't cover.
Okay, I appreciate it.
Yeah. Okay, all right. So today we are going to continue what we were doing last time and finish that up. We're going to do just one example. The main idea of last class was that if we're given a continuous function on a closed interval, is very important, that we can find the absolute maximum and minimum values of that function. And to do it, there was a method, there was a procedure that we followed. And I just want to do maybe one more example. Did anybody have maybe a question, you know, from the homework that you want me to work out, or should I just pick one randomly here?
Actually, I was wondering if you could do, let me find it. Number 27.
Yeah, I mean, I can do 27. That's not quite as difficult as I wanted to do, but I'll do it. This function is really a nice function, so there's not, the algebra in this is not as bad as some of the other problems, but I'll work it through. Okay, so all you're asked to find here are the critical numbers. That's it. That's all you're being asked for in the homework. Find the critical numbers. So that just means we want to figure out where the derivative of this function g is 0, and we want to figure out where the derivative doesn't exist. So the first thing we need to do is take the derivative. That should be pretty straightforward now. Hopefully everyone's got the power rule down here. So there's your derivative. And now let's set it equal to 0. So when we set it to 0, we take that function, set it to 0, and we have to realize that we can factor this. We can factor a t out. And then the next thing we do is we try and factor this, because this is a quadratic. So let's see if it factors. Does that factor? Let's see, 2, maybe 2t, t. I don't see that factoring. Yeah, I don't think that factors. So if it doesn't factor, then you'll have to use a quadratic formula. You with me? This gives you an answer, t is 0. And then this one, we have to set equal to 0 and use a quadratic formula. So our solutions are negative b plus or minus the square root of b squared minus 4 times a times c. All of that over 2 times a. Understand what I'm doing there, Brian?
Yes.
Okay. And so then from this, something interesting is going to happen underneath the radical here. You're going to get 9 minus 16 times 2 is 32. And that's going to give you a negative number underneath the radical, which means that there are no solutions to this, because you can't take a square root of a negative number.
You can't
So
make it.
Pardon?
You can't make it into a complex number.
Well, I mean, we could, but everything that we do in calculus does not deal with complex numbers. That goes for Cal 1, Cal 2, and Cal 3. You never deal with complex numbers or imaginary numbers until you get into a class called complex analysis.
Okay.
So whenever we get an imaginary number, we just give up at that point. We say no solution.
Okay. Thank you.
Mm-hmm. So right now we have t equals 0. And then the other thing we need to do is figure out where it doesn't exist. But the derivative in blue here is a polynomial function. And so it's defined everywhere. There's no values of t that would cause any problems. So we only have one critical number. Is that okay? Questions? Okay, any other requests from homework?
When you said you were looking for like a complicated one, do you mean one with like fractions?
Just something that's polynomials are easy to take derivatives of, easy to set equal to 0. You know, this is all just stuff from algebra. Things that are more complicated are things that would require like product rule or quotient rule when we take the derivative. Yeah, I mean, I did 7 examples last class, so I think I gave you a good mixture. Here was one with a tangent in it. Here was one with a natural log. We did one with a square root with a product rule. We did one with a quotient rule. We did a polynomial. We did another polynomial. So I think I've given you a good mix. Okay, well, we're going to get more practice because not the section, not 4.2, but 4.3, we're going to have to do more of this. Okay, so let's for now move on to 4.2. 4.2 is going to be kind of a quick section. I'm hoping I can knock it out in 20 minutes, maybe 30. So this section 4.2 is about this thing called the mean value theorem. And we abbreviate it MVT, all right? So mean here doesn't mean like you're a mean person, like you're not nice to people, right? This mean means average, okay? Like when you talk about the mean of something, you're talking about its average. So you could look at this as being the average value function. So I'm not going to get into a bunch of the details here. I want you to try and understand this theorem visually first. So before I get to the mean value theorem, there's a theorem called Rolle's theorem. And most students have no problem understanding Rolle's theorem. Okay, so let's just look at Rolle's theorem visually. Rolle's theorem says that if you have a function, hold on. All right, got I don't know why it does this. Give me a second. It's always something here. Okay, try it again. Okay, so if let's say we have a function that starts at A, ends at B, and that function is continuous. So it's continuous on a closed interval, meaning we can draw it without picking up our pencil. If I tell you that the height of the function at A, okay, so how high this is, that's actually f of A. If I tell you that that height is the exact same height as that at the end, so where it starts and ends have the same height, if you draw any curve between those 2 points, do you all agree that there is some point somewhere between here and here, somewhere in here, that when I look at the slope of the tangent line at that point, it will be parallel to the line connecting those 2 points.
Yes.
Does that
Yeah.
make sense to you?
Yeah.
Yep.
I'll draw another one over here. So let me just say I start at A and I'm going to end at B, but I have to end at the same height. Now I can draw any curve I want. So I'm just going to make up a curve here. Do you all agree that there's somewhere in here that when I go and look at the slope of the tangent line, it'll be parallel to the line connecting these two?
Yes.
It looks like maybe about right here, right? I have the slope of a tangent line there. And there looks like there's another place right here. So we had two places. Do y'all see that? Where the slope of the tangent line is parallel to the horizontal line connecting the two.
Yes.
That's Rolle's theorem. Rolle's theorem says you have to have that. Okay, so now let me read you Rolle's theorem. It says, let f be a function such that first, it's continuous on a closed interval. So that means you can draw it without picking up your pencil. Also, it's differentiable, meaning that you can take the derivative of this function and it makes sense. And then the last thing says, well, no, the third condition is that f of a equals f of b. That means the two endpoints have to be the same height. It says if those three conditions are true, then there must exist some number c somewhere inside where the derivative at that point is equal to 0. Now, the reason it's equal to 0 is because remember, a horizontal line has a slope of 0, right? So it's saying that the derivative would then have to be 0 somewhere. So again, here we draw function and, oh, sorry. We draw a function however we want. Here's A, here's B. There must exist some point C, I think it's about right here, that if I go up to there, the slope of the tangent line must be 0, which is parallel to this. Okay, that's Rolle's theorem. Now, the mean value theorem is just another way of looking at Rolle's theorem. Are there any questions on Rolle's theorem, though? Does it make sense to you that you would have to have that somewhere, have a parallel line like that?
Yeah, but what's that like useful for? Like,
Was that a question, Austin?
yes, like what would we use that for? Like where can that be applied? Like,
Okay, yeah, so let me get to mean value theorem. Okay, so the mean value theorem is basically take Rolle's theorem. I'm going to show you the picture first. Take Rolle's theorem. Okay, here's the same picture I showed you. I said that, hey, you know, somewhere in there, you've got to have some point that is parallel to this, right? The mean value theorem says, imagine that you have a function that doesn't necessarily start at the same point and end at the same point. So what if we tilt this? You see how now these don't end at the same, they're not flat? The mean value theorem says, well, look, we're still guaranteed that there must be some point in here where the slope of the tangent line is still parallel to this line. So, but you notice that that line's not flat anymore, right? So what we're saying is that somewhere in here, there's a C that when I go up to that C and I look at the slope of that tangent line, the slope of that tangent line is f prime of x, sorry, f prime of C, because we're at C here. That must be equal to the slope connecting these 2 points together. Now, if you go back to college algebra, the slope that would connect these 2 points together would be the rise over the run. And the rise is going to be the difference in the y coordinates. So it'd be this, take away this. So that's your rise, it's your f of b minus f of a over, and then your run would be the difference of these, so you put b minus a down here. And that's what the mean value theorem says. Now, to answer your question, Austin, like where would this be used? What this is saying is this. Let's say you take a road trip, okay? Let's say that you take a road trip and you go 60 miles on this road trip. And let's say it takes you 1 hour to do it, okay? You go 60 miles in 1 hour. Then what was your average speed?
60 miles per hour.
60 miles per hour. So the way we could visualize that is if this is time and this is distance, you started your trip here, you're traveling, you're doing something, and then you wind up at the end here after 60 minutes, you went, sorry, yeah, I'll do hours. After 1 hour, you went 60 miles, right? Your average speed is going to be the slope of the line connecting those 2 points together, because your rise is 60 and your run was 1. So the slope of the line connecting the 2 endpoints is your average speed, right? Which is what you told me, 60 miles per hour. What the mean value theorem says is somewhere in there, somewhere in here, so at some C, you have to be parallel to that line, which means what? If you, at some point in your trip, you had to be doing what?
The average speed.
You had to be going the average speed. Okay, if your average speed for the trip was 60 miles per hour, the mean value theorem says, well, then you had to at some point have gone 60 miles per hour. It's impossible for you to average 60 miles per hour and never have gone 60 miles per hour. Okay, that's what the mean value theorem says, is that you must achieve your average value somewhere. There's a slope of a tangent line that rate of change, that, you know, the slope is a rate of change. That rate of change in here is somewhere in there. It's going to be equal to the rate of change on the entire trip. Now, there's other things that I could do to show you this. I mean, there are huge implications of this theorem. It's one of the most important theorems in calculus, but you really don't see it until you get to Cal 2, how we use this, unfortunately. Okay, so what our goal right now is, I'm going to give you a function, and then I'm going to ask you to go find the C. I'm going to want to know where the C is that makes that the mean value theorem guarantees you. All right, so let's try a problem. All right. Oh, I forgot to put the state the mean value theorem. So mean value theorem, not Rolle's theorem. Okay, mean value theorem says, let f be a function such that f is continuous on a closed interval. It's differentiable inside. Then there must exist some point C. Okay, there must exist some number C in there such that, now that's not very big, but it's right here also, that the slope of the tangent line at C must be equal to this is like the slope of the line connecting the 2 endpoints. Somewhere those must be equal. Okay, so I'm going to copy this and bring it over to our work so I can use it whenever it's time to do this example here. Okay, so that's what the mean value theorem guarantees you. All right, so let's start with the problem. So I want us to verify the mean value theorem for f of x equals negative x cubed plus 4x squared on the interval 1, 2. Make it 1, 3. Okay, so let me show you visually first what's going on here. Oops. Try this again. Okay, so we have this function, negative x cubed plus 4x squared. So negative x cubed plus 4x squared. And we're only looking at this on, what did I say, 1, 3?
Yes.
Okay. There it is. Okay. So now what we are trying to do now is this. We are saying that if we were to connect these 2 endpoints together right here, there's some x value. Now the x-axis is down here. It's hard to see it. There's some x value in here, which we will call C. Somewhere in here, there's a C. I don't know where it is yet. That when I go up and I take the slope of the tangent line there, it should be parallel to that black one. Okay, we need to go find that value of C. We want to know where it happens. Does that make sense visually? Yeah. Okay, so let's do it. So here's what I need. I need this to be true, right? That's what has to be true. So let's make sure we understand a few things. For the mean value theorem to work, we have to have a continuous function on a closed interval. So is this a continuous function?
Yes.
Yes, because it's a polynomial. Okay, all polynomials are continuous. So that's a continuous function. Here's a closed interval. Okay, well, let's take its derivative because we're going to need the derivative to use the theorem. So the derivative of this is negative 3x squared plus 8x. Now, I'm not setting that equal to 0, okay? I'm not setting that equal to 0. What I'm doing is I'm trying to figure out if there's a number that I can plug into this that'll make it equal to this. Now, this part we have to go figure out what it is, okay? That's that black line that connected the two endpoints. So we need to understand that in the problem, this is A and this is B. These are our two endpoints. So I need to know what f of B, f of 3, minus f of A, f of 1, over B3 minus A1 is. Understand? I'm going to figure this out. So f of 3 means plug 3 into the original function. So what happens if we plug 3 in here? I'll try and do it quickly. Minus 3 cubed plus 4 times 3 squared. Let's see, negative 27, 9, 4 plus 36. I'm getting 9. You'll get 9 there? 9 for this?
Yeah.
Okay, now plug in 1. So what happens if I plug 1 into that? I have negative 1 cubed plus 4 times 1 squared. This is going to be negative 1 plus 4. So that should give me a 3. So minus 3 over 3 minus 1, that's 2. And so we wind up getting 6 over 2, which is 3. Okay. All right, now here we go. Here's what we want. We want to find a C such that f prime of C equals 3, right? We want the derivative at some point to be equal to that slope. Now, f prime of C means take the derivative and plug C into it. And look what you have. This is a quadratic equation in C, isn't it? You can move
Yes.
everything over to one side. And then you can solve this using the quadratic formula. So this is like the A, the B, and the C, right, in the quadratic formula. So I'm going to move quickly through this. The solutions are negative 8 plus or minus the square root. Let's see, B squared minus 4 times A times C, negative 3 again, all over 2A. So for here to here, I'm using quadratic formula. And this will give me negative 8 plus or minus square root. Any questions? Get my calculator ready here. So this is 64 minus 36. All of this over negative 6, which equals negative 8 plus or minus, let's see, 64 minus 36 is going to give you 28. And then we're going to have to take the square root of that. So negative 8 plus or minus square root 28. So 28 square root, I get about 5.29 over negative 6. And finally, I have two different answers here. I have the plus and the minus. So I'm going to look at both of these cases. So I'm going to do negative 8 plus that, and then divide by negative 6. So one answer I get is 0.451. Now let me do the other one, -8 minus 5.29 divided by -6. And I get 2.215. I got two answers. Any questions on the answers, how I got them or anything? So do I have two answers? I mean, I have two answers, but is my final answer going to be both answers?
One might work, but one might not. What if
Yeah, one doesn't fit in the what's it called?
within
You'd
the
have to find it
interval,
between 1 and
right?
3, don't you?
Yeah, it has to be between 1 and 3,
Yeah.
which means that
The first one
you're
doesn't
going to
fit.
throw out the first one. The mean value theorem guarantees you at least one. You could get two answers. In this particular case, we got two answers, but we're only going to use one of them because of the interval. So C must be 2.215 right there. Now, does anyone have a question right now? I thought I heard someone ask something.
I was just wanting to know that when we're figuring out using the quadratic formula and we end up with a negative under the square root, do we just say no, like this doesn't exist, or is there something that always exists? Or
Yeah, no, you would just say no solution. If you had a negative under the root, you would just say no solution.
okay.
Yeah. Now, if you were working this problem and you got that, you would be, that would be be like a red flag that you've done something wrong, because the mean value theorem guarantees that it must be there. You must have some point. So 2.215, let me go back to this. Let me see if, let me try, I'm going to graph a line x equals 2.215, just so you can see where it is. Okay, so again, if I were to connect this, you know what? This allows me to draw lines. I've never really done this before. Oh, shit. Stop. Stop. Okay, hold on. This is not working. Erase. Try it again. Okay. I forgot that I could draw lines on here. So if I connect those with the straight line, right? What we're saying is that if we were to go to the point right here on the graph right there, that point, if we were to get the slope of the tangent line there, right, it would be parallel to this one. Okay, and actually the slope would be 3. We know that because remember, that's what the slope of the black line was. It was 3. Okay, that's it. That makes sense? Okay. So for mean value theorem, what we're doing, just to recap, mean value theorem, I give you a function, I give you a closed interval. We go back to the work. I give you a function, I give you a closed interval, I ask you to verify the mean value theorem. So what you do is you first make sure it's a continuous function, then you take its derivative. You just hold off on that. You go calculate this right here, f of b minus f of a over b minus a. You go calculate that, that'll be a number. You're using a and b. These are the endpoints of your interval. That'll give you some number. Then what you do is you plug c into the derivative and set it equal to this number, and then solve that equation. All right? Any questions? I'm going to do one more example. How about this one? Verify the mean value theorem for f of x equals the natural log of x squared plus 1 on the interval 0, 4. Okay, I'm going to go look at the picture first, all right? Just so you can see it. So we have natural log of x squared plus 1. And we're going on 0, 4. And let me get rid of this one. Okay, so here's the graph. Okay, here's the graph. If I were to take this and connect a straight line here like this, right? That's that f of b minus f of a over b minus a. That's the right side of the mean value theorem. We're trying to find the value of c somewhere in here, that if I went to that point on the graph, the slope of the tangent line would be the same. Okay, so that's what we're trying to do visually. So what I'm going to do first is take the derivative. So that, oh, well, is it continuous? Hold on, we should check that. Is this a continuous function? Well, natural log has problems. You cannot plug 0 into the natural log and you can't plug a negative in. Do y'all agree with that? All logs have domain restrictions. Can't plug in 0, can't plug in negatives. But that's okay because look at what's inside of this. X squared plus 1. X squared plus 1 is always going to be positive, won't it be? You square any number and add 1, you've got to be a positive number.
Yes.
So we don't have any domain issues here. So I know it's a continuous function because there's nothing I can plug into it that's going to cause a problem. So I take its derivative. The derivative of this is 2x over x squared plus 1. Chain rule, right? The derivative of natural log of something is 1 over it times the derivative of what's inside of it, which is 2x. And I slid the 2x up top. Is that all right?
Yes.
Okay, now we need to come over here and let me grab from the other page that formula. There it is. So we have it. Oh, I know what's going on. What? Okay, I'm all out of whack here. All right, so here's our formula. So let's figure out what this side is first. For us, that'll be f of 4 minus f of 0 over 4 minus 0. Yes? Okay, so now at this point, we're going to have some weird numbers here. When you plug 4 into the original function, 4 squared is 16, plus 1 is 17. Natural log of 17 is going to be the top left corner. Minus, now let's plug in 0. 0 squared is 0, plus 1 is 1. And so we get natural log of 1. And then all of that over 4. And unfortunately, we're going to need the calculator for this. And by the way, natural log of 1, everyone here should know natural log of 1 is 0. All right. So, but I do need the decimal of natural log of 17. So natural log of 17 on my calculator, I get 2.833, and on the bottom I have 4. So I divide that by 4, and I get about, it's approximately 0.708. So now I'm going to say, all right, I need the derivative of the function at c to be equal to that. So the derivative of the function at c just is plugging in c for x, must be equal to 0.708. And now I have to solve this. So the way I would solve this is I would clear the fractions. I'd multiply both sides by c plus 1, or sorry, c squared plus 1. That would cancel them out here. I get 2c over here equals, then I distribute that through. So 0.708 c squared plus 0.708. And then I'd move everything to one side because again, we have a quadratic equation. I'd make sure I put it in descending order. That's highest power of x, highest power of c, and then just keep decreasing the powers. Everyone okay with that? Just bring 2c over so it becomes negative. Quadratic formula now. So remember, I've got, this is A, that's B, that's C. So here we go, quadratic formula. Negative b plus or minus the square root of b squared minus 4 times A times C all over 2A. Okay, I'm going to do all of this on my calculator, and then I'll just tell you what the final answer is here. Not the final, I'll just do this 2 plus or minus. When you do all that square root stuff, you should get 1.412 all over. Uh-oh. Shit, I hit the wrong button. 2 times 0.708. So 1.416. So there we go. I'm going to have two different answers. And one of these answers better be inside 0.4. I might have more than one answer in the interval, but we're about to find out. So I'll do the plus and the minus. Does anyone have any questions? I know I'm going a little bit fast here.
It's pretty straightforward.
Okay, good. It's just computational, right? You just got to make sure you don't mess up any signs.
Yeah.
Who said that? Yeah.
That was me.
Okay, yeah. All right, so I got two answers. And both of them live inside of the interval 0.4, don't they? They both live there. I'm going to go check with the picture. 2.41 and 0.415. 2.41, and then the other one was 0.4, what was it?
0.415.
415. Did I mess this up? No, 0.15. Okay, so here we go. These are the 2 points. It looks like if I were to connect this to this endpoint like that, do you all agree that if I went to this point right here, come on, draw. Draw. Why is it not wanting to draw? Damn it. Oh, my pen stopped working. That's really weird. If I draw a tangent line here like this, it's parallel to the black one, and then the other one is up here at this point. If I draw a tangent line here, it looks like it's parallel to the black one. So we actually had two places where it happened. It could be more than two. Mean value theorem guarantees one. Okay, and again, this goes back to the trip. If you drive 60 miles, it takes you an hour. I guarantee you went 60 miles per hour at some point in your trip, but you could have done it twice, 3 times, 100 times. It just depends on the path. Okay. All right, any questions? We're going to move on. I got to figure out what's going on with my damn thing. I don't know why it doesn't like me right now. Y'all ready for this semester to be over? Y'all looking forward to the end?
It never ends.
Okay.
For sure.
All right, try it again.
Wait, I do have a question on this one.
Yeah.
Since 0.415 is negative, that doesn't fit in the interval 0.4. So why did we qualify that one as an answer?
This one does. 0.415. The interval is 0 to 4.
But isn't that like our negative answer off of the quadratic?
Oh, no. Okay, so no, it's not a negative 0.415. It's when you use this negative, you go 2 minus 1.412. When you do that, you get a positive number, and then you divide it by a positive, you'll still get a positive. The plus and the minus
okay.
here is just to tell you how I got them. The first one was me doing 2 plus this, and then dividing by this, I got that. And then I did 2 minus this, then divide by that, and I got this.
Okay, okay, I see.
Yeah, it doesn't mean I'm gonna get one positive and one negative answer. Follow?
Yeah, that was
Okay.
just on me.
Good. Okay, that's it. That's mean value theorem. There's another problem, but I think it'll take too much time. But I'm going to pose the problem to you. Maybe if we have time, some other class or something, I can revisit this. But this is a good question for you to think about. Okay, so let's say that I have two cars, car A and car B. This is from the top looking down, and they're on a racetrack. There's the start line. And here's the finish line, okay? Someone's gonna, wave the flag or whatever and say, go, and both these cars take off, right? They start racing down the track. And they're racing. And here's what I'm gonna tell you. At the very end of the race, they tie. I mean, like precisely tie. I have two questions for you. The first question is there some speed that both cars had to have gone?
Yes.
Wouldn't that be average speed?
Their average speed. So car A had to at some point in the trip go its average speed. Do y'all agree with that?
Yes.
Whatever car A's average speed was, at some point in the trip, car A had to look down at their speedometer and see their average speed, yes? And can you say the same thing for car B? Car
Yes.
B at some point had to go its average speed, yes? But don't they both have the same average speed?
Yes.
They both started at the same point. They both ended at the same point, and it took them both the same amount of time. So that means that car A had to go its average speed, but it also had to go car B's average speed. Yes? That makes sense?
Yes.
Yeah.
Okay, so here's the second question. I already answered the first question. My first question was, is there some average speed that they both must go? Yes, there is. They both must go their average speeds, and those happen to be the same because they went the same distance over the same time. So just to make things easy, just so you can really try and visualize this, let's say, just to make it real easy, that this was 60 miles, okay? I know that's crazy. And let's say that it took them both 1 hour, right? Then at some point in time, right? At some point in time, car A had to be going 60 miles per hour, yes?
Yes.
And at some point in time, car B had to be going 60 miles per hour, yes?
Yes.
Was it at the same point in time?
No.
No.
Doesn't have to be.
Not necessarily.
So does anyone not understand my question? They both went 60 miles in 1 hour, which means they both had to at some point be traveling 60 miles per hour. I think we all agree on that. But my question was, does that 60 miles per hour happen at the same moment in time for both cars?
No.
And I'm getting a lot of no's. So let's take a poll.
Quick question. Do you mean like during the race, at some point they were both at 60 miles per hour?
Well, we know that because the mean value theorem, car A went 60 miles in 1 hour, and therefore at some point in time, car A had to be going 60 miles an hour, right? Had to,
Okay.
right? Car B went 60 miles in 1 hour, and so that there's some point in time for car B that it was going 60 miles per hour. My question was, is that happening at the same exact moment in time for both cars? Is the 60 miles per hour happening at the same moment in time?
Well, the 60 miles per hour, like they hit it at the same exact time, like
Yeah.
same exact.
So look, imagine your car
Exact
A,
place?
right? Hold on, your car A, right? Your car A, you're driving. At some point in time, you look down at your speedometer and it has to read 60. At some point in time, guaranteed, it has to. Okay? Car A. And let's say that happens, let's say for car A, that happens at TA. That's the time for car A. That's when it hits the 60 miles per hour. And then car B, you're driving, and at some point for car B, it happens, they look down and they see 60 miles per hour, and that's time for car B. My question is, are those two times the same?
So I put no on
There
the
is a possibility.
Does it matter the placement? Like say like A was like ahead at the same time? They have like how can they be ahead? But I don't know.
The question is just, does it happen at the same moment in time?
I think
So, Austin, what do you got?
I put no on the poll, but I think it actually does. The more that I think about it,
Okay.
because
Yeah. The more I think about it too, I was like, yeah.
I'm underdogging it. I think yes.
So here's the deal. Right now, 80% of you think no. It doesn't have to be the same point in time. 20% of you say yes. I can tell you right now that we could spend the rest of the class debating this. Someone could say, the people who say no could sit here and argue all day long about their reasoning for it, okay? And the people who say yes could try and argue their reasoning for it. And we would get nowhere because both sides would have decent arguments. This is what math is here for. Math is here to make it where there's no questions. And I'm going to tell you the answer is yes.
Woo! I knew it.
I knew it.
Okay, but how do you prove that, right?
Got it.
How do you prove it?
Nothing to do with
So you can sit here and verbally tell me why you think it is, but you have to be able to show it mathematically. So I don't know, man. I've gone this far. Should I just show you?
yeah.
I can just show you.
So are these cars built the exact same?
It doesn't matter. The cars don't matter. It could be any object, racing it. All that's relevant is that they started together, they ended together. That's all that's all that you need. And then you also need that the car didn't like just vanish and like disappear into like some like time warp and come to another spot on the track without moving. Like it's got to be continuous, right? The car has to like be what you would expect a car to do, not disappear, right? Not jump through time. As long as you can assume that, then we're good. Okay, so I'm going to show you how to prove it, all right? I think some of you will follow this, some of you won't, and it's okay if you don't. It's not something I'll test you on, but this is something to show you how we can use math and the mean value theorem to answer a question about something that is very hard to justify verbally. There's 80% of you, well, now it's down to 70%, that think that no, it can't be the same point in time. It doesn't have to be. I'm telling you, it has to be the same point in time. So here's the proof. You ready for the proof? Okay. So I'm going to draw a graph because it'll be easy to show if I do a graph. Okay. So the first graph that I'm going to draw is car A. All right. And this is going to be time and this is going to be distance. Okay. Here comes car A. Car A starts out the starting. And then after 1 hour, it's going to have gone 60 miles. Agreed? So I've got to get to this point. And I can get from this point to this point as long as I connect it with a continuous curve, right? Because the car is not going to disappear. At every point in time in the trip, the car was somewhere. So it doesn't matter how I draw this. Let me just draw it. Okay, there it is. So that is car A. Now, let me draw car B. Do you agree that car B has to start at the same point and end at the same point? Yes?
Yes.
Okay, and now I get to draw that however I want. Okay? That's car B. Do you agree that car A's path is a continuous function? Car B's path is a continuous function. I'm going to create a new function. And this is the part I don't think you would have thought about. Most people don't. I'm going to create a new function, and I'm going to call this the D function. And the D function stands for difference. I'm going to take the difference of the two. I'm going to define this to be car B's position minus car A's position. So let's look at the beginning. At the beginning, what is the difference between their positions?
0.
Nothing. So I'm going to plot 0. At the end of the trip, after 1 hour, what's the difference between their positions?
0.
0.
Nothing, right? 0. Okay. Now, in between, from here to here, do you agree that maybe car B is in front of car A and then car A might be in front of car B? They're going to go back and forth. Who knows what's going to happen in the race? but it should be continuous. Whatever this is, it should be a continuous function. And I've got to connect these 2 points together, right? Do y'all agree with that?
Yeah.
Yes.
Okay. What?
Say, why did we put car B first minus car A?
It doesn't matter.
Doesn't matter.
You can
Okay,
put
yeah.
car A first
Sorry, I
or
wasn't-
car B, doesn't matter. The important thing is that they start and end at, this new function I created, D, starts at 0, ends at 0 on the y-axis.
And then-
Now, the mean value theorem guarantees me a C where the slope of the tangent line will be 0. Do y'all see why it has to be 0? Because these 2 points are connected together like this, right? So there is some C such that D prime at C must be 0. Do y'all agree with that? Okay, but wait a minute. D prime is really just the derivative of D, right? And since D is made up of car B's path and car A's path, and they're being subtracted, then D prime really means the derivative of car A, or sorry, car B, this derivative minus the derivative of car A, that must be 0. See, because again, this has to do with derivatives. If you define a function to be the difference of 2 functions, then the derivative of that should be just the difference of the derivatives. That's critical. Y'all still follow this? But look, if I just add car A's derivative to the other side, I get the derivative of car B must be equal to the derivative of car A, right? Because it comes over and becomes positive. And that means, what does the derivative mean? The derivative would give us the speed, wouldn't it?
Yes.
So what we're saying is that at some point C, those 2 derivatives are the same, which means that the speed of both cars are equal at some point C. It might even happen twice, but it's guaranteed to happen at least once. That's it. So that proof, I mean, like nobody in this class comes up with that proof. And this is still not a very formal proof. I think it's enough for you to understand, but it's still not written the way a mathematician would like to write it, okay? Okay, all right, we got to move on. I hope that answers part of Austin's question, like what's the value of this? The mean value theorem can be shown in that case to answer a question that really otherwise it would just be debating back and forth, you know, just your view versus my view, and that doesn't work in the real world. Okay, we are now going to 4.3. We're now going to talk about derivatives and how they tell us about the shape of what a graph looks like. Okay, so somehow the derivatives, when we look at derivatives, they tell us about what the graph looks like, right? And so we're going to have some definitions here, and I think most students have an okay time with this. So let's look at this first part. If the derivative of a function is greater than 0, that means positive. The derivative is the slope of the tangent line, right? So if the derivative is positive, that means the slope of the tangent line is positive. That should mean that when you're looking at the graph is going up. And so anytime we see that the derivative is positive on some interval, then we know that the function is increasing on that interval. So here's an example. Here's a function in blue. And back in college algebra, we would say that this is an increasing function because as we move from left to right, like the way we read a book, as we move from left to right, the function keeps going up, right? Up, up, up. And you can tell that by looking at the slopes of the tangent lines, any point that I pick in here, do y'all see that the slope is positive? I'm having the computer calculate the derivative for me. Slope is positive, 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 no matter where I am. So positive derivative corresponds to an increasing function. Negative derivative is the opposite. If you have negative derivatives, then your function must be going down. If your derivative is 0, this should say equals 0. I don't know why I did not put, I didn't change that in my code. That's weird. It's been like that for years and I've never caught that. Hold on. I'm gonna fix it now. Okay, so if your derivative is 0, 0 means flat line, right? Then that means that as you move across, the function must be constant. Okay, positive derivative going up, negative derivative functions going down, 0 derivative function is flat. Here's a function that changes, right? So look, pay attention to the derivative. As we move from left to right, derivative is positive, positive, positive. We get to the top. We get to the top. When we get to the top of that hill, right, our derivative is 0. Then we move, keep moving. Now my derivative is going to become negative, 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 negative. Keep going till we get to the bottom. Now the derivative is 0. And then it switches back positive, 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 positive. And now we're increasing, right? So do y'all see how that derivative changed over the function? Positive derivative, negative derivative, positive derivative. So this section is about how the derivative tells us about what a graph looks like. If we can tell something about the derivative, we can kind of start to get the shape of the graph. Questions?
We're not drawing it, right?
We're not drawing it yet.
Oh.
We are going to draw functions, but not yet. What was the other question?
Could you go back to the first graph real quick?
That one?
Yeah, I just wanted to take a little screenshot of it.
Oh, okay.
I got it, thank you.
Okay, so this brings us to what's called the first derivative test. This is a very important test for the next few sections. All right, suppose that C, that's some value, some number, okay? Suppose C is a critical number of a continuous function. So what are we saying? C being a critical number means what? That at C, the derivative is either
0 or doesn't
0
exist.
or doesn't exist, all right? So let's say that we're looking at some point on the graph where the derivative is either 0 or it doesn't exist. Then here's the test. If the derivative changes from a positive to a negative at that point C, then we have a local maximum there. Think about what this is saying. If your derivative changes from positive to negative, positive means going up, right? Negative means going down. So if your graph goes up and then down, right, at some point, then you've got to be at the top of a hill or something. This is an example. Look at this right here. Do y'all see the maximum point right there? Get over here. Y'all see that little local maximum? Notice that to the left of that point, the derivative is positive. And then when we get to the top, it's 0, and then it switches. See, it becomes negative. So I put green over here to show you derivatives positive, going up, up, up. Here, derivatives negative, negative, negative. So now we go down, local maximum. What about here? Do y'all see at this point right here? Let me make this a little bigger. Do y'all see at this point right here, the derivative would be 0? I'll go to it. Do y'all see the derivative is 0 here? Now, to the left of it, what's the derivative? To the left of that point, what's the derivative? Positive or negative?
Negative.
Negative. How about to the right of that point?
Negative.
Negative. If it goes from negative to negative, doesn't change signs, we don't have a max or a min, local max or min. It has to be a change in sign. You can see it happen right here. We have a local minimum. Look at what the derivative does. Negative, 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 switch to positive, positive, positive. So the test is, Positive to negative is local max. Negative to positive is local min. No change in sign, you don't have a local max or min. Basically, what this is, everyone, is a way for us to find local maximums and local minimums. This is how we do it. We have to run this test. Okay, I'm gonna do an example. Y'all aren't very responsive to this. Are y'all okay or what? What's going on?
Yeah, I mean,
Okay.
it's pretty straightforward.
Okay, I'm gonna just, yeah, let's go with 5x cubed minus 3x to the 5th. And I want to find where, I want you to find where f is increasing and decreasing and any local max or mins. I'm going to graph it first. 5x cubed minus 3x to the 5th. 5x cubed minus 3x to the 5th. There it is. Okay, you see that graph? Now I want us to take a step back. This is a polynomial function. In college algebra, you would have been asked to graph something like this. And in college algebra, what you would have determined in college algebra is you would have determined the x-intercepts. You would have determined that the left side goes up and the right side goes down. You would do this thing called the leading coefficient test to do that. You would also figure out whether or not you cross through these x-intercepts or bounce off of them. And that was called the multiplicities of the zeros. And if you're sitting there going, what the hell is he talking about? I understand it's been a while, but I'm just saying this is something we did in college algebra. What we never did in college algebra was actually figure out exactly how low that point went. You could never find that in college algebra. And a good college algebra professor would have told you, you need calculus to do it. And that's exactly what we're about to do, everyone. We are about to figure out this point and this point. And that one, we're going to figure out that that's going to be a point also. But we've finally come to the point in the class where we can identify these peaks and valleys on functions. And we're going to use the test to do it. All right. So here we go. All right. So what we need to do first is we need to find the critical numbers. So that means we need to take the derivative. We need to set it equal to 0. We need to figure out where it doesn't exist. So here we go. Derivative. (15x squared minus 15x to the 4th). Now, where's this thing 0? Well, I take it and I set it equal to 0. I can factor out a 15x squared. I'll be left with 1 minus x squared. And I can keep factoring. 1 minus x squared is 1 plus x, 1 minus x, because that's a difference of squares. And then I can set each of these equal to 0. So 15x squared equals 0 is one equation. 1 plus x equals 0 is another equation. 1 minus x equals 0 is the other. So we have 3 answers. X is 0. X is -1. And x is 1. Any questions? Those are critical numbers so far. Where does the derivative not exist? Or does it, or do we even care about this?
It doesn't matter.
Yeah. Because the derivative is nice, right? The derivative is a polynomial. So this is never going to have a problem. We're not going to have division by 0 or square roots of negative numbers or anything like that. So we only have 3 critical numbers. All right. So at this point, we need to start thinking about the first derivative test. The first derivative test said that if our derivative changes from a positive to negative, then we have a local max. If the derivative changes from negative to positive, we have a local min, right? That's what it said. So we're going to try and come up with like an efficient way to do this. And I have the way that I do it, that I've always taught my students. This is not usually the way the book does this, but they do it in a slightly different manner. And it, as a student, this was one of the points in the textbook that confused the hell out of me. So I'm presenting this to you the way that it makes sense to me, and most of my students have no problem with this. So here's what I'm doing. I'm going to draw a number line. I'm going to plot my critical numbers. 0, 1, and -1. And then I'm going to put dotted lines above those. And what I've done is I've broken the number line up into four different regions. Do y'all see that? And what I'm asking myself is, what is the derivative doing over here? What is the derivative doing right here? What is the derivative doing right here? And what is the derivative doing right here? I need to figure out, is it positive or negative? Right? That's kind of the idea that I'm thinking through this, right? So to figure out what the derivative is doing, I'm going to pick any number I want, to the left of -1. I'm going to pick -2. I'm going to circle it so you don't confuse it with this one. I put an X on it so that you realize that's going to be what I'm referring to as a test point. I want to test that point into the derivative and see if the derivative turns out to be positive or negative. Then I'm going to pick another test point here, maybe like -1/2. Then I'm going to pick another test point right here, like maybe +1/2. And then I'm going to pick another test point over here, like maybe 2. You can pick any number you want, as long as it's in between, or, you know, anything to the left of -1. You could have picked -100, doesn't matter. Just as long as it's to the left of -1. Any number between here and here, any number between here and here, any number here. So now the testing. I'm going to test these into the derivative. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. One more, 12. Into the derivative. These test points are not getting plugged into the original function, okay? They're going into the derivative because we want to know what the derivative is doing, right? Positive derivative means up, negative derivative means we're going down. Okay, here we go. I need to plug in -2 into the derivative. I need to plug in -1/2 into the derivative. I need to plug in 1/2 into the derivative, and I need to plug in 2 into the derivative. And here's our derivative right here. I'll bring it down here just so we have it. Okay, so there's my derivative, and we get to plug these numbers in. I'm going to do the first one, but then I don't know if I'm going to do all of them, because this is tedious work. So this is going to be 15 times -2 squared minus 15 times -2 to the 4th, which is 15 times 4 minus 15 times 16. All I really care about is that whether or not this answer is positive or negative. Can somebody tell me if it's positive or negative?
Negative.
It's
Negative.
negative. It's negative. Okay, so that's a negative sign with a little circle around. That's a negative number. All right, it's a negative number. So I'm going to come back up here, and remember how I had a little question mark here? Now I know what the derivative is. The derivative is less than 0 here. It's negative. If the derivative is negative, what is the original function doing over here then?
Going down.
It's going down. So I'm going to write below this. That means the original function is going down over here. I'm put a little arrow here. Okay. The derivative being negative means the original function is going down here. Questions? We got to plug in these now, right? Now you could just plug it in here, couldn't you? Yes? It's a pain in the ass, but you could. There's a little bit of a shorter way though. Look at this right here. I'm going to grab this version of the derivative. Let's see if you can follow me on this. This is the faster, more clever way of doing this. This is my derivative just factored. So let's just think about what would happen if I took -1/2 and plugged it in here, here, and here. So what would happen if I did -1/2 and squared it and then hit it with a 15? I'd get a number that's positive, wouldn't I?
Yes.
And then I'd multiply that times a number right here. Now, if I put -1/2 here, what's 1 plus -1/2?
Positive.
Positive, right? So that's positive. Okay, now what's 1 minus -1/2?
Positive.
Positive again. So if I take a positive, multiply times a positive, multiply times a positive, that answer should be
Positive.
positive. So I know that this is just going to be a positive number. Why could we not do that here? Why could I not have done that same thing here?
Too complicated.
Yeah, it's because it's subtraction. Okay, that's why. Think about this. If I told you if I said, hey, guess what, everyone, that number is positive, and then I want to subtract from it another positive number, let's just say. Can you tell me whether or not that's positive or negative?
Negative. Not yet.
No, you don't know enough, right? This could be 3 minus 4, that's negative. It could be 3 minus 2, that's positive. So you can't do it here. You can only do it in the factored form because then it's multiplication. And multiplication, you can tell what happens. Let's see, maybe we can do the same thing for this one. What about if we took this one and plugged it in here, here, and here? Let's see if we can work quickly through it. 1/2 here squared.
Positive.
Positive. Okay, I'll have a positive times. Okay, 1/2 in here.
Positive.
Positive. 1/2 in here.
Positive.
Positive again. Let's just do the last one since we're getting through these. Let's plug 2 into here, here, and here. So when we plug 2 in here, we get
Positive.
positive. 2 right here,
Positive.
positive, and then 2 right here,
Negative.
negative. Okay, so that's the first time it switched. Okay, let's figure out what these would have been. 3 positives multiplied together, positive. 2 positives is a positive, but then you hit it with the negative and now it becomes negative. Let me go back and fill this table in. Remember, I had these question marks. I didn't know what the derivatives were doing. But now I know that when I go -1/2, I get a positive number there. The derivative's greater than 0. When I go to +1/2, I get a positive also, it's greater than 0. When I go to 2, I get a negative, so it's less than 0. This means the original function, since the derivative is positive, is going up here. Here, the derivative is going, or sorry, the original function is going up. Here, the original function is going down. Questions? Let's see if we can't answer the question now. Find where the function is increasing and decreasing in any local max or mins. Let's start with the increasing and decreasing, and I'll begin with increasing. Our function is increasing here and here, right? Because our derivative is positive and our function must go up there. That's increasing, right? So the way I'm going to write that is this. I'm going to try and keep this all on one page. This is going to be my answer over here. F is increasing. I like to put an arrow next to it on the interval -1 to 1. So please note, everyone, these are X values that I'm giving you. Okay, I'm giving you the X values for where the function is going up. So between -1 and +1, my function is going up, 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 right? How about where it's going down? Here and here, right? But when I say here, I mean here this way forever and here this way forever. So the way I need to write that is f is going down. Let's look at this first one. Everything to the left of -1. To the left of -1 forever.
Negative infinity to -1.
Negative infinity, comma, to -1.
And then you do like a U letter.
Then you do a union symbol, good. And then now you need everything from 1 to the right. 1 to infinity. So we're trying to get the x values where we're going up, the x values where we're going down. No questions?
Yeah, why was it so crucial to have 12 exclamation marks?
Okay, the reason why I did this is because you know how I picked these test points and I told you, I'm telling you, plug them into the derivative? Because on 4.1, right, when we're finding the absolute max and minimums, right, we have a closed interval. On that method, you get your critical numbers and your endpoints, and what do you plug them into?
To your original location.
To the original equation. What happens is students start doing this and they pick these test points and then they forget what they're doing and they go plug them into the original function. That's not what this is about. This is about plugging into the derivative to see if we're getting positive or negative. So you have to distinguish between section 4.1 and section 4.3. 4.1, closed interval method. You plug everything into the original function. 4.3, we're looking for local maxes and mins. You plug all your test points into the derivative to figure out what's going on. Oops. Okay. So we have answered the first two questions, where the function is increasing and decreasing. Now I need to find any local maximums or minimums.
Could these numbers switch?
What do you mean?
Like if we write down a -1 comma negative infinity instead of
No, it has to be from left to right, the way you'd read a book.
Okay.
So like your number line, negative infinity is to the left. So you go negative infinity to -1 and then union 1 to infinity. Okay.
Thank you, sir.
Okay. All right, let's talk about local maxes. Do we have any local maxes? So what are we looking for?
Where it switches, or like from like from increasing to
Positive?
increasing.
From
Yeah.
increasing to decreasing, right? I mean, look at it. Can you see it here? The little up and then down, right? I mean, can you all see that this really means that our function does like that,
Yes.
right? It goes up and then it comes down. So we should have a local max. Where is it occurring?
At 1.
At x equals 1. So we have a local max at x equals 1. Now, do you want to know what the actual value is? Like, do you want to know how high it is? Okay, just plug that 1 into the original function. So plug 1 into the original function here. If I plug 1 in here, I'll leave it to you, but you'll get 2 here. In other words, if we look at the point 1, 2, this point is going to be a local max. Don't confuse the point with the interval. Do we have any local minimums? So now we're looking for down and up. Do we have any?
Yeah.
That'd be
At
negative.
x equals -1, right? Because we're going to go down and then we're going to go up. Down and then up. So if I plug -1 into the function, I believe, what do we get? -1, we'll get -5, and then we'll get +3. So we'll get -2. So we -1, -2 is a point on the graph. All right, so what about at 0? The function went up, then up, right? It didn't go up then down, it didn't go down then up, it just went up and up. So something is happening at 0, but it's not a local max or min, right?
D, oh, D and E, it's like no change, I guess.
Yeah, we don't have a name for it for the first derivative. We actually are going to have something else similar to it in a minute, but or not today, but next class. Okay, let's go back to the picture. All right, this was our graph, right? And now if you see here, we found that point right here, 1, 2. We found it, right? We said 1, 2 would be a local max. We found the point -1, -2. We found that one. We also know that there's something happening at 0. It's a little odd. Oops, that's not 0, that's O. There's something happening here, but it's kind of like, it's not a local max or min. So I hope you can see now our derivative, we were going down, 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 down. Then we got here, now we're going up, 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 down, 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 right? We figured all that out, right? We figured all that out without needing the graph at all, right? We could do that purely using calculus, right? All we needed was the derivative. And that is the power of the derivative, because this works for any function. It's not just polynomials, it's for any function. So that means that if you ever have a function in the real world where you're trying to find where the little peaks and valleys are, then all you have to do is find the critical numbers, pick some test points, figure out where you're going, up, down, down, up, and you'll find them. That is a huge, huge deal. I think I'm a little more excited about it than you are, but it's a big deal, all right?
Now, if you were to ask us one of these questions on the test, is that the notation that you would want us to put our answers in?
I'm okay with any notation that makes sense, but that's the notation I'm going to continue to use. I'm going to always use interval notation for where it's going up and down. So here's another problem. I want to give you maybe 7 minutes, 8 minutes to just find the critical numbers. See if you can even find the critical numbers for this in the next 7 minutes. What do I mean, find the critical numbers?
What do you mean?
Yeah, what do I mean?
Oh, like what was the question?
You need to find a derivative.
Yeah, derivative for.
Yeah, so here's the instructions. I want you to do this, okay? Find where, same instructions last time, but the first step for this is to get the critical numbers, right? So take 7 minutes, see if you can find the critical numbers, and then I'll come back and I'll see what you got. Well, I won't see, I'll just ask. You're going to see the algebra here is not as easy as the previous problem, all right? Would you all like me to write down the derivative and start setting equal to 0?
Sure.
Okay, I'll start working it out, but I'll let you keep going.
Oh, that's where I stopped. My bad. I kept going. Oh wait, no. Okay. My bad.
So for those of you who are looking at what I'm doing, I've taken the derivative with the power rule. And then I realize I have to set this equal to 0 at some point. So I'm trying to clean this thing up. So I'm taking the x to the negative 1/3 and I'm dropping it down to the denominator. And the reason I'm doing that is because I'm going to try to put these two together as a single fraction by getting a common denominator. This is all because I have to set it equal to 0 at some point.
Just a random question. I got the same answer you did, but could we have gotten rid of the fraction by introducing like a 1, like a 3 into it?
I'm not sure what you mean by introducing a 3.
I think she
something
means by
else.
multiplying the entire thing by 3 to
Yeah,
cancel out the 3 on the
to
bottom.
cancel out the 3s. Yeah.
Okay, you could not multiply by 3 because you would change the expression. You could factor out a
Okay.
1/3. That you could do. You could factor out a 1/3. You could factor out a 10/3 in the beginning. Like you could have algebraically done this, pull a 10/3 out, and then have x to the negative 1/3 minus x to the 2/3.
That's
You
what
could
I
have
did.
done that, but you can't just arbitrarily multiply by 3.
Got it. Thanks.
Okay. One more line, then we'll talk. Okay, what do y'all think? Any questions on what I did here or why I did it? The why is probably more important, you know?
How could you do this?
What's that?
How could you do this?
What do you mean?
No, I was supposed to say is like as an alternative to y.
Yeah,
Sir.
I was thinking a different way. Never mind.
look, at the very beginning, if I had stopped right, let's say here, let's say I'd stopped here. And then I said, okay, set that equal to 0. Right, because we have to figure out where the derivative is 0. So if I do that, I'm going to have problems because like, how do we do this, right? Like, how do we set this equal to 0? So knowing that I'm going to have to set this equal to 0, I'm trying to get it turned into one fraction. Because I told you, I'll remember that a fraction can only be 0 if the numerator is 0. Remember me telling you that? So I try and rewrite everything as fractions first. Then I say, oh, I need a common denominator here. I'll introduce an x to the 1/3 here. That gives me the common denominator. And then when I multiply those two, I add the exponents. 2/3 and 1/3 is 1. So that gives me an x up there. Now I have the same denominator, so I put the numerators together. And now this is a very nice, clean version of the derivative. Would y'all agree? It's a very nice looking derivative. And now I'll set that equal to 0. So that means I set 10 minus 10x over 3x to the 1/3 equal to 0. But that means all I have to do is set the top equal to 0, because I've told you all that already. And that just means that 10 equals 10x, which means x is equal to 1.
What if we just factor out that 10 over 3 and then keep all the other stuff? I mean, that x to the 2 another power is in the parentheses. What could we do after that?
Yeah, you could have done that and then just, did a common denominator, same thing, put it all together. You just would have had a 10/3 out front.
Okay, got it. Thank you.
Yeah, so if you would have factored out 10/3, here's what it would have looked like. It would have been this. There. That's what it would have been.
Yeah, okay, that's what it looks like. Thank you.
Okay, so I've figured out where the derivative is 0. Now, very important, I need to know where the derivative doesn't exist. Look at the derivative. Is there anything I cannot plug into the derivative?
Oh, it's at the bottom, right? You can't
Zero.
put in 0.
0, right? We
Zero.
cannot have 0 on the bottom. Now, can you have 0 in the original function? Look at the original function. Can I plug 0 in here and 0 in here? Yeah, right.
I mean, you
I
probably
mean,
could.
wouldn't it just give you 0 again?
It would just
I
give
don't
you
know.
0 though. It wouldn't give you division
Yeah.
by 0, right?
Right, it's just gonna be
0 to the 2/3, 0 to the 5/3. That's just going to be 0. So you can plug 0 into the original function, but you cannot plug 0 into the derivative. And that's a problem. So x equals 0 is a second critical number because of the denominator. So I have 2 critical numbers total. I draw a number line. I place my critical numbers on the number line. I partition my number line in now to 3 separate regions. I'm going to pick 3 test points. -1 looks good. 1/2 looks good. 2 looks good. And where do those get plugged into?
The derivative.
The derivative. And what I'm looking for is whether or not I get a positive or negative number out when I plug these into the derivative. And when I say the derivative, I mean this. I want to plug those numbers into that right there. By the way, everyone should be aware that x to the 1/3 really means the cube root of x. Okay.
Yeah.
All right, so let's try and do this. If I plug -1 into the top, what happens if I plug -1 into the top? What do I get? 10 take away 10 times -1.
You get 0 at the top, right?
You get what? No, you'll get 10 take away 10 times -1. That's 10.
Oh, plus that.
Yeah.
My bad. I was like, hold on. I don't know.
That's all
how to
right.
do
So you get a
this.
positive on the top. What do you get on the bottom? If you do -1 in here, what's the cube root of -1?
Imaginary.
Nope, that's square root. Be careful.
Oh, -1.
-1. Cube
would
root
be
of -1
negative.
is -1 still, and then times 3, you get -3. So that's a negative on the bottom. And a positive divided by a negative is negative. So if I plug -1 into the derivative, I get a negative number. That means over here, my derivative over here is negative, which means my original function must be going down over here. We're running out of time. I got to plug in 1/2 now. Okay. So if I plug 1/2 into the top, 10 minus 10 times 1/2, 10 times 1/2 is 5. So 10 minus 5 is a positive on top. Now on the bottom, what's the cube root of 1/2? I have no idea, but it's positive, isn't it?
Yeah, it's positive.
It's positive. Cube root of a positive number is positive. So I'm going to get a positive times 3 that'll still be positive. And a positive divided by positive is positive. That means the derivative here is positive, which means the original function here is going up. And then I plug in 2. Okay, now I'm running out of time, so I'm just going to tell you what happens. You get a negative number, which means that the derivative here is negative, which means that the original function is going down here. Okay, questions? I'm almost out of time.
For the derivative.
Hey, just FYI, I've got a TV on here. It looks like the jurors reached a verdict on the trial that's going on.
Oh.
I just got a notification on my phone.
Yeah, so we'll see if America can keep their shit together today. We'll see what happens. I hope everyone's okay no matter what happens. Okay, let's see here. Let's figure out where the function is going up. Okay, where the function is going up, that happens in here, right? In the yellow region. That's the only place that the function is going up. So that's going to be on the interval 0, 1. The function is going down where? Left of 0, right of 1. Be real careful. Some of the mistakes students will make is that on these intervals, they'll accidentally use the test points. The test points will never be part of your answer. It'll always be the critical numbers. Okay, so just be careful with that. So I'm going to have negative infinity to negative 1 union 1 to infinity. Questions on that? How about local max? Do we have a local max? What are we looking for? What are we looking for?
Down.
What goes up and then down? Does it ever go up and then down?
Yeah.
1 at x equals 1. Now, if we wanted to know the actual value of the local max, we would plug 1 into the function, the original function. And if you plugged 1 into here, you would get 3. So that means this point 1, 3 should be a local max. Do we have a local min?
Yeah, it's a 0.
Yes.
At 0. And so that's going to be the point. If we plug 0 into the function, we should get 0, which means the point 0, 0 should be a local minimum. All right, you ready? I'm going to graph it and we'll call it a day. Let's see.
So what's the trial you were talking about?
What's that?
What was the jurors trial you were talking about?
Officer who.
Yeah. It's just go look it up. You'll find that. I commend people who are unaware of it. That's a good thing. It's less stress in your life. X raised to the 2/3. Oops. Okay, 5x to the 2/3 minus 2x to the 5/3. Now that's a pretty cool looking function right there, isn't it?
Yeah, it's cute.
And look what we have. We said that it will be decreasing. I'll do decreasing in red. Decreasing to the left of 0, right? Decrease, 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 decrease. Where else was it decreasing?
From 1 into infinity.
Yeah, from 1. So it's decreasing over here, right? You see it? And we said that it'll be increasing between 0 and 1. That's here to here. We see that. Here's our local min. And here's our local max. We found all of that without a picture. Okay, so for homework, what I would recommend that you do for your homework assignment for this session, this is a very important section, all right? This 4-3, very important for what we're going to be doing next few classes. Next few sections. So I would say focus a lot of your attention Let me just see here. Okay, so for all these problems, every single problem that you see here, they all have multiple parts, part A, B, C, D. For all those problems for homework, just do parts A and B. Part A says find where it's increasing and decreasing. Part B says find the local max and mins. That's what we've been doing. We're only halfway through this section. So next class we'll come back and we'll do the other part of this section, and then you'll be able to answer parts C and D. Okay? All right, everyone. I will see you on Thursday. Thursday? Yeah. Have a great day.
Wait, is today? Oh my God, today's not Thursday?
No.
Oh my
No,
God.
It's the first day of the week class.
Yeah.
Oh
Dang.
Lord.
Yeah.